Hello and welcome to the Turing podcast. This week we're bringing you an episode all about astrophysics, exoplanets and supernovas, which was recorded before the coronavirus outbreak. Thanks for listening.
You're listening to the Turing podcast, a production of the Allam Turing Institute, the UK's National Institute for Data Science and Artificial Intelligence.
Hello and welcome to the Turing podcast. My name's Effie and I'm here with
Ed. Hi guys.
Hi. How are you doing today, Ed?
I'm very good, Effie. How are you?
Yeah, I'm pretty good. I'm pretty excited for today's episode. So do you know who we're talking to today?
Today we're chatting with Tarek, Allam and Gordon Yip, who are both on placements here at the Allam Turing Institute, but they're PhD candidates in the Department of Physics and Astronomy at University College London. And so we're going to be talking about astrophysics things with them, specifically supernovas and exoplanets.
I think that's probably why I'm so excited today. This sounds really cool. I can't wait to talk to them. But before we do that, do you want to have a quick look at the news?
Yeah, I've got an interesting AI-related story that I've picked up in the news this week.
Okay.
It's quite a relevant one. It's quite one of global importance, actually. We've got a sort of global problem of antibiotic-resistant bacteria.
Yeah.
It's a problem that's ongoing. We're always having to look for new antibiotics. And some researchers at MIT are claiming to have discovered a new antibiotic. But crucially, they've discovered it using AI.
Right.
So
what's it called?
It's called Halicin. And it was originally a drug that was investigated as a treatment for diabetes.
Right.
But by training their AI system to spot molecules that prevent bacterial growth, they've then applied that AI system to a database of drugs, including this one. Okay. And it's been identified as something that could have antibiotic properties.
Right.
They've gone on to test it in mice, and it does seem to kill a range of bacteria, including some which are resistant to current antibiotics.
Okay, I think that's really cool. Do you know how they trained how they made this discovery exactly?
Well, yeah. So their AI system uses what's called a neural network, and it's been trained specifically to recognise the properties of molecules that prevent growth in bacteria.
Right.
And then once that neural network had been trained, they can then look at the properties of drugs which are in this particular database. I think it was called the Drug Repurposing Hub. And that's exactly what they've been able to do. They've identified those drugs which don't look like structurally like current antibiotics, but which the AI system predicts should work as antibiotics. And they validated, as I said, in mice that it does work in this case. Okay,
so is this? My key question is this story? Where did you find it? First of all,
well, it's been in a couple of places. It was in the Guardian. It was also in Nature.
Cool.
I believe the research paper was in Cell, the journal.
Good stuff. So, really pressing question. Is this something that I would find on the Just Says in Mice Twitter feed?
You might do. It's at that stage at the moment. It's been tested in mice, but it needs to go through to the next stage, which will be clinical trials in people. Okay. Nonetheless, it's a very exciting discovery because if it's a proof of concept that new drugs can be discovered using AI, then this might be just the first of many.
Great. I mean, we talk often here at the Institute about the future that AI is building. I think this is a classic example of how our health is going to be vastly improved by intelligence that is artificial intelligence. I think it's called.
Well, it's not
this new thing. Have you heard
it's
of
not
it?
Something that people might think of. You think of AI, you don't necessarily think finding new drugs. It's not the first thing you think of. But it does seem to be an application that's growing in the amount of research that's gone into it.
Yeah, I mean, so for anybody else that's interested in this kind of stuff, if you look on the Turing website, we've got lots of impact stories where you can find more information about the research that is taking place at the Turing and beyond into how to improve health and medical sciences. And it's definitely a major focus for us.
It's a big evolving field, health data science and AI.
Great stuff. Well, on that note, I think maybe we're ready to talk to Tarek and Gordon. You ready?
Let's go for it.
Let's go.
All right, welcome Tarek and Gordon. Thanks for being here.
Thank you for having us.
So how long are you two both into your PhDs now?
It's coming up to third year, must be.
Yeah.
So we're both on a CDT. So the first year is courses, and then you sort of get into your PhD research.
Okay.
And so altogether the program's 4 years. So I guess we're coming up to our third year now, right?
And you're both in the same year then?
Yeah.
Same cohort, same year.
Yeah.
What's life like in the Department of Astronomy? Is it this Department of Astronomy and Astrophysics?
That's it. Yeah. So we're sort of currently sat at opposite ends of the building. So Gordon, you're working on, what was it? Planetary.
Yeah, exo-planets, planets basically outside the solar system.
Okay.
That's my domain, yeah.
Yeah, and so I'm sort
exoplanets and your supernovas.
Yeah, supernova. That's my game.
Which one is better?
Oh, there's a competition.
Is there a better one? Yeah, is there a better one, or is there?
Supernovas are a lot bigger.
That's true.
Yes, I like it.
A lot more explosive as well.
Yes. Yeah. Whereas exoplanets are, what would you say about exoplanets if you had to compare the two?
Well, definitely. For starters, we get more funding.
Yeah, you've got me there.
Because people are interested in it. So naturally, we got more funding.
Right.
Yeah.
Okay. I mean, that's fair. That sounds like exoplanets has beat you out with it's all about the money.
Being smaller, there's got to be a lot more of them as well.
Yeah.
Infinite number of planets out there. I'm going to kick off with a question about supernovas.
Go for it.
For you, Tarek.
Yeah.
So your PhD research looks at the classification of supernova light curves. But first, let's ask, what is a supernova and why are astrophysicists interested in classifying them?
Right, awesome. So a supernova, you can just think of it as an exploding star. Okay. So as a star sort of comes to the end of its life, it goes boom, and we see a supernova. Now,
there's no sound in space. So
no.
It doesn't really go boom, right?
No, exactly.
Being pedantic. But
Yeah. No. So if you what we're trying to do, we're trying to classify the different types of exploding stars. And the one that we're specifically interested in is type 1A supernovas. Now, type 1A supernovas occur when you have a star and it accretes some mass. So it's pooling in some mass from a companion.
And then another star?
It's
sucked in another star?
Yeah, it's sucking in another star, but then it gets to a critical point. And when it gets to that critical point, it can't sort of support itself under its own sort of weight, its mass, and then it just implodes and explodes. And so we're really keen on identifying these ones because we know, well, through theory and physics, the energy we expect to observe from this explosion. And so because it's a very determined energy that we expect to observe, we can use this as what they call standard candles. So it's almost like having if you think of a 100-watt light bulb and I put it in front of your face and you sort of know the distance between that light bulb, if I move it across the room, you can work out the distance of how far I've moved it because the brightness that is given off is still 100 watts. But the luminosity you observe would appear dimmer because I've moved it far away. And so you use the same sort of thing here. So we use them as standard candles because we know the energy, we know the light we expect to observe. And so by observing how much dimmer it is, can give us a proxy measure for distances in the universe.
Is that because the supernovas are expected to always give out the same amount?
Exactly.
Of
So
energy?
Same amount of energy. There's sort of some hand wavy stuff sort of going on here, but to a sort of like, you could say a normalization factor, we expect to see a certain amount, and judging by how much dimmer it is from what we expect,
you can judge the distance.
You can exactly. And so why it's sort of very interesting is that as you'd expect it to follow, shall we say, a linear relationship. Well, it's actually an inverse square law. So as in, you move it twice the distance, the luminosity should decrease by a factor of 4, if that makes sense.
It's 4 times dimmer when it's twice as far away.
Yeah, exactly. But what was sort of observed is that as you go further and further away, and this also means sort of looking further away in time as well, so because you're sort of looking back, the further you're looking away, it was observed even dimmer than what we would expect from the relationship of what the equations tell us. And so for that to be the case, there must have been some kind of expansion or something to have occurred. And this sort of sparked the whole search for dark energy. Some form of energy is driving this expansion. And so if we can find more type 1a supernova at increasing distances / high redshift, then we can add more data points to our sort of to the sort of the graphs that we have and get a better understanding of what this dark energy might be. It allows us to constrain certain theories. So I'll just drop in right here. I don't deal with the theories. I'm the data guy, but yeah, this is why people are very interested.
Well, if I was to try and get you to explain exactly what is dark energy, then
that's a no. I'm walking out now. Yeah,
but basically, it's what we think is powering this expansion.
Yeah, exactly.
These objects are dimmer than we think they should be.
Yeah, exactly. And so the idea is that if we can find more of these type 1a supernova, then we can constrain the theories of what this dark energy might be, and answer the big questions. Yeah, that's the idea.
So okay. Go on, you ask a question. You've got a question, go on.
Sorry, I got too different. So how often do you get this kind of type 1a supernova?
Type 1a events?
Yeah.
So that I won't be able to give you a proper answer for. But I do know that, so the issue sort of facing the field at the moment is that we only have about on the order of 1,000 spectroscopically confirmed type 1a supernova. So all that means is when you see the explosion, you take a spectrum of the light that you're observing, and they'll often use this as the sort of, this is historically the way you classify what kind of supernova it is, because the spectrum tells you what elements are present or were present during the explosion. And so that tells you exactly, okay, this is a type 1a, this is a type 2, blah, blah, blah. But doing that process is very time consuming and it's very expensive. And so what they're hoping to do now is use a different method, so photometric methods. So you observe the light coming from the explosion, and you'll observe it over different pass bands, so large filters. And this allows you to sort of collect more light, easier, quicker, and cheaper than a spectrogram. And so you'll hopefully be able to observe a lot more of them sort of going forward. So I'm not sure what they expect, but we're hoping with upcoming surveys to see many orders of magnitude more supernova. Yeah.
Okay. Well, that sort of leads on to my next question, which is, well, at the Turing podcast, we're interested in how the era of big data is changing science. So when it comes to astronomy, how big does this big data get?
I'm glad you asked me that. I happen to have my notes right here. So in the case of LSST, so the Large Synoptic Survey Telescope, which has recently been renamed the Vera Rubin Observatory, I believe. So that is going to be looking for, using photometric methods, looking at supernova. In fact, actually, it's going to observe the transient sky. So as the sky is changing, because the idea with the LSST is that it's going to do a full sky map every 3 nights and then come back and sort of do that again. And so over the period of 10 years, you'll get a movie of the sort of living and breathing universe. And so that experiment, although it's not completed yet, is expected to receive 15 terabytes of raw data per night. We're expecting on the order of 10 million transient events, alerts per night. And so these kind of data rates...
What do you mean by a transient event?
Okay, so something that changes in time. So in the case of a supernova, its brightness is changing in time. So you'll take an image of the sky, and then you revisit that patch, take another image, and you've seen that the amount of light that you're observing has changed. You see that it's all of a sudden it's brighter now. So that would be a transient event. It's changed. And so we're expecting, on the order of 10 million of these per night.
Okay. So you're looking at the night sky every night, and you're seeing 10 million differences in the brightness of stars, and including supernovas.
Exactly.
That's a lot of data.
It's a lot of data. And so it means that there's a lot of processing that needs to sort of go in place. Now, so whilst we can still use photometric methods, and so, this is the easier and cheaper of the way to sort of classify things, you still can't beat a spectrogram. So what you would like is in real time, when you've observed an alert, is to be able to direct spectroscopic resources to also go look at this event, and can you confirm, right, what supernova is this? So there's a lot of work, being done to do photometric classification, but you still can't beat a spectroscopic classification.
How does the ordinary spectroscopic classification work?
Right. So with a spectroscopy, you have, if you think of your light spectrum, you'll just have a bunch of bands appearing as if they're missing, and these are sort of absorption lines of where different elements are absorbing the light in that sort of spectrum. And so that is a proxy to tell you what kind of elements are present. Because if you can see that, okay, the absorption line for oxygen is in your spectrogram, you know that, okay, well, oxygen has caused that absorption line. And so the reason why it's so good is because it tells you exactly what elements are present, and we know from different types of explosions have and have not certain elements. So that tells you straight away. It's like, oh, well, we see that. And
that presumably factors into how you classify them.
Yes,
based on
exactly
their elemental composition.
Exactly.
Based on their spectrum of light.
Yes, yeah.
Well, that sort of, I think we can follow on from that by asking Gordon a question, which is how can we use the same sort of thing to determine the chemical composition of exoplanets when we're looking at them?
That's actually a very similar technique that we're using. And I think in astronomy, we're sort of using, other people's technique as well. So in exoplanet, we are looking at, so one of the things that we are looking at is the chemical composition or the atmosphere of the exoplanet. Basically, can you tell that whether there's any clouds on it, any H2O water, CH4 methane, etc., etc. And we do that by actually looking at a particular type of event, which we call it transit. So for a transit, what is a transit? So imagine that you have a star like our sun, then you have a planet passing in front of it. Then all of a sudden, if you're looking at this event, then the brightness coming out or the light coming out from this system is actually reducing when the planet is crossing in front of the star. And like Tarek just said, if you look at this event in different filters.
So these are basically like sort of eclipses in their own, not our solar system, but in those systems.
Yes, that's exactly what is happening. Yeah, and if you look at this kind of eclipses event in different wavelengths, then you can basically capture the molecular absorption feature, and that's how we infer that there might be some kind of water, HCO2, etc., in there.
Whatever other compounds might be in the atmosphere of those planets.
Yes, exactly.
And so in that process, you don't have any way to gather any specifics. It's all entirely theoretical based on what you do know.
Yes, that's one of the troubles. That's always based on what we know about our chemistry and how it behaves in this kind of temperature. But then the problem is that the molecular feature that we usually encounter in the laboratory is always like room temperature, or sometimes you may have like 100 Kelvin. That's the sort of range, like 100 to 500 Kelvin. But
just for our listeners, so what's 100 Kelvin in Celsius? So it goes down to 200 minus 250 or something like
minus
that?
273, yeah. So
So it's really cold.
we might get Dan to have a look.
Oh, our producers, it says it's minus 173 degrees Celsius, so that's very cold.
Yeah.
That's for COK, right?
Yeah.
That's almost as cold as Canada.
Yeah.
Yeah, but then sometimes in some exoplanet you may have like 1,000 K, 1,500. That's like really, really hot, and then we don't have anything, an example or any specimen that has this kind of temperature or this kind of molecular.
So behavior. How do you account for those discrepancies? What do you do in those instances?
Well, you go to the theory and then you just calculate purely from the theory.
I see. Okay.
Yeah.
So I'm guessing it's because obviously on Earth we don't have those temperatures, so we don't know exactly what sort of chemistry occurs at those temperatures.
Yeah.
Yeah.
So that's one of the trouble. Our only blueprint is the solar system.
Okay.
Yeah.
That's pretty cool. All right, so I feel like this is a good opportunity to ask some questions of Gordon. So, as you've already explained, exoplanets are any planet that exists outside of the solar system as we currently know it.
Yeah.
Do you have any idea of how many have been discovered these days, or really how fast they're being discovered?
So right now we currently have like about 4,000 exoplanets being discovered, but with many more candidates waiting to be confirmed.
Right.
Yeah.
And how many more?
Oh, that's a tricky question.
Presumably these are all on sort of nearby solar systems, or
sorry.
Well, I don't know. Yeah, I don't know what constitutes nearby, but I'm guessing there have to be stars that are relatively close to our solar system.
Yeah, in astronomy, nearby is very, very vague.
It's a relative term,
It's next door.
Compared to the universe, everything's very nearby. So actually, most of the exoplanets that we're discovering is actually within our Milky Way.
Right.
You may find some of them in other galaxies, but only a few. I think there are about 8,000 or 6,000 waiting to be confirmed.
Wow,
for
okay.
now. Yeah.
So really, what you're saying is that we were all misled at a very early age to believe that our solar system is just this small number of planets, and there are all sorts of additions that will be included over time. Is that what you're saying?
Yes, there will be many, many more.
Okay.
Yeah.
Interesting. All right. So
there won't be any more in our solar system, I don't think.
You sure?
Yeah.
Oh, but
I don't know if we can believe
there's
that.
this talk of like finding Planet 9. I have no idea what it is. I feel like they're sort of everyone's sort of upset about Pluto being demoted, so they
that's
need
what I was going to
a ninth.
This might be an interesting, fun question for the two of you. Do you have a take on the Pluto controversy and what other? How big does a planet have to be a planet?
Right. So I'm not a planetary scientist, but I'm going back to the old school days where I was taught that Pluto was a planet. So I'm sticking by that.
Yeah.
So you both believe that Pluto is a planet?
Well, I'll put it a different way. I won't say I believe it's a planet, but I'm going to say it's a planet.
Okay, all right. I think I understand where you're coming from.
According to the rules of IAU, it's not a planet. To me,
it's going official now.
Yes. It doesn't make a difference.
I feel like, Ed, do you think Pluto's a planet?
Well, I'm not a planetary scientist either, but my understanding is that there are other objects that have been discovered in the solar system that are as big or bigger than Pluto, and there's quite a few of them. So that's where the controversy arises from.
Yeah.
But thinking outside the solar system, there's about 4,000 roughly, we reckon, or things that we can see within our Milky Way so far. That actually strikes me as not that large of a number, because there must be, I don't know, how many, are we talking about millions of stars in the Milky Way, or?
Yeah. If you think about, the number of stars compared to the number of planets, you find out, 4,000 is basically a very, very small number. And I think that's basically because we are limited by the technology that we are having.
Right.
Okay.
Yeah.
It's not that they aren't out there.
It's not that they're not out there. It's actually one of the statistical study carried out by researchers. And then they say that you have at least one planet per stellar system, per solar
Right.
system out there.
I feel like this is a really good time to ask, how is machine learning supporting your efforts? Can you tell us about the atmosphere of exoplanets and how you're using machine learning to find out more about that?
Okay, so basically in the future, we'll have many more missions coming online into space, and then looking at exoplanets and looking at their spectra produced by them. But the problem is you have basically 1,000 of them or even more. Now, you can't really look at each one of them and say, oh, it has water, or maybe that one has CO2. So you need some sort of automated tool to actually help you define it. So at UCL, what we are trying to do is we are trying to train a new network, something like CNN. And then what we're going to do is we use the spectrum, and then we ask a new network, okay, from this spectrum, can you help me to predict some kind of, does it have H2O, and how much H2O is there in the spectrum?
Right, okay.
Okay, so this is another sort of classification problem, I suppose.
Yeah, both classification and regression, because you want to know about whether it exists or not, and if it exists, can you tell me about how much water is in there?
Right. So how well are we doing these days with making those predictions on the 4,000 or so exoplanets?
To
And
be
how
honest,
quickly are we doing it?
not really.
Mm-hmm.
It's early days.
It's the very early days. We only have a spectrum of 30 planets.
Okay.
And then even in those 30 planets, we can only say, okay, it has water. Okay, it doesn't have water.
Right, okay.
That's it.
And that's how you're classifying it. It's either you have water or you don't, and that's it.
Sorry?
Sorry, I didn't quite catch that last bit. You were saying something about water.
Water, yeah. Yeah, you can only say whether that planet has water or not.
I see.
Yeah.
Okay.
Not how much it has.
And not how much, and therefore it's
Not
very
how
difficult
much,
to.
yeah.
Oh, okay.
You have a huge uncertainty on that, yeah.
Right. Well, hopefully your methods will be perfected and we'll soon know how much water there is on exoplanets and how much carbon and other, life-giving materials there are on other planets. Which leads me to my bonus question for the two of you.
Ooh.
It's a fun one. As experts in astrophysics and astronomy,
You know when somebody starts with "as experts," it's a good question.
what is your opinion on the question of are we alone in the universe? Let's go to Tarek first.
Going to Tarek first. So I think the statistics make me feel that we're not alone. I feel like it's just there's too many stars and too many potential planets that surround these stars for there not to be life elsewhere. The key thing though is there intelligent life out there? So as in we're saying, okay, is there life? But are we saying, is there life like us out there? That is a question I have no idea about. But I feel biologically, surely by the statistics of how many stars are out there, there's got to be life out there. Yeah, so we're not alone.
But you thinking it's too far for us to reach or for it to ever reach us?
I'm going to sadly say yes, just by the distances involved. To think that sort of our nearest star is like 4.6 light years away.
Right.
And so the distances involved are just kind of crazy. So I feel like, at least in our lifetime, we might be lucky, I don't know. But it's very unlikely that we'll sort of get any sort of signals back. So I need to be careful of what I say because there's a massive
controversy around.
Yeah, exactly.
Yeah.
But my personal belief is that we're not alone. But I'm not expecting a call from ET anytime soon.
Okay, well, that's slightly disappointing.
Sorry,
maybe
guys.
Gordon's got a different
Gordon's
answer. Yeah, what's your answer?
Sadly, I have to agree with Tarek.
No.
That I think that there should be life somewhere in the universe, but the problem is the distance making us in a long distance. Let's say in a long distance relationship that we can't really reach each other.
Yeah. Okay, well, I mean, I feel like that was partly Partly an inspiring answer, partly disappointing. If they exist, we just can't access them, is what you're saying.
Yeah.
Well, let me ask just a tangent question from that. What about maybe not advanced life in terms of human type intelligent civilizations, but some form of biochemistry or microbial life? I mean, we haven't found anything yet, right? But it's still possible that, like, on one of the moons of Jupiter, or certainly in some of these exoplanets, that we'll find something eventually.
Yeah, I think actually there are studies that is suggesting that the moons of Saturn or Jupiter, they might actually have life because they have underground ocean in one of the satellites, one of the moons. I'm not sure which. Tarek?
I'm going to say Europa.
Yeah,
50.
Europa.
Yeah.
I've heard Europa's the icy one with water underneath.
Yeah, it is.
It's a very scientific description.
Yeah.
On that note, I think we'll wrap up there. Tarek and Gordon, thanks very much for coming on the podcast.
It's been a pleasure.
Thank you indeed. Thank you very much. Any final words?
Oh,
No?
Blimey, no.
Okay, we'll direct ET in case ET is...
Are either of you
Let me know if he calls. I
are
want
either
to
of
say
you
I'm sorry.
active on social media? Do you have Twitter
Oh,
accounts
yes,
you wanna-
follow me, Tallam JR on Twitter and all my sort of social media.
And how's that spelled?
TALLAMJR. I almost messed up my own name there on the spot. But on Twitter, GitHub, all your favourite social media.
How about you,
Fantastic.
Gordon?
I'm a little bit social media isolated. I don't have a Twitter account yet, but I should get one.
Yeah.
Okay.
Okay. Well, in the meantime, is there anywhere that we can find your work? Anything that you want to push or plug?
Oh, actually, I've got a GitHub account that
Okay.
can follow me. So my GitHub account is Gordon Yip. So GORDONYIP.
Yep.
427.
Great. Well, you heard it here first. Thank
And
you very
there
much.
is actually a project that I want to plug. I'm not fully involved, but I just think the technology involved is really awesome. And it's dealing with all this, the data rates that's coming from LSST. So the project's called Fink, Fink. Google it, put in some stars and astrophysics and you'll find it. But yeah, awesome project run by a team in France. So
Okay.
check it out.
Thank you very much, guys. Thank you, Tarek. Thank you, Gordon. And thank you, everyone. Yeah.
Thank you.
Thank you.
You're welcome.
To learn more about the work going on at the Alan Turing Institute, visit our website at turing.ac.uk. To get in touch with the podcast team, if you have any questions or suggestions, email us at podcast@turing.ac.uk.
Music for this episode was provided by Jamin Sun. You can listen to his latest releases at jaminsun.bandcamp.com.
The Turing Podcast is hosted by Ed Cowstry, Tarek Allam, Ben Walden, Effie Dennis, and produced by Dan Whitfield for the Alan Turing Institute.